Hello everyone, my name is Xian Wang. Today I'll be presenting our paper titled Backpropagation-free Network for 3D test-time adaptation. Test-time adaptation enables model to adapt to new data during inference time while maintaining their effectiveness in dynamic and evolving environments. This capability is crucial in scenarios where 3D data plays a key role. Such as in autonomous driving, robotics, or augmented reality, where conditions can vary dramatically. So those challenges like changing lighting, weather, seasonal changes, or corruptions can significantly alter the characteristic of the input data. What's more, collecting 3D data in real time is often very expensive and limited, and any small inaccuracies early on in the network can accumulate, leading to reduced accuracy and reliability over time. So, to address those challenges, we propose the backpropagation-free network for 3D test-time adaptation, or BFTT-3D, which adapts to changing conditions without the computationally intensive process of backpropagation. This approach is especially beneficial for 3D data, as it helps to reduce the complexity and computational costs. Our BFTT-3D framework mainly consists of three components. First, the non-parametric network is used to capture the sample feature for source and test data. Then the subspace learning is used to effectively reduce the distribution variance between domains when constructing the similarity matrix. Finally, the adaptive fusion module aims to balance outputs from different branches based on entropy. At first, in the preparation stage, we utilize the non-parametric network to extract the general feature from source point cloud. This network relies solely on non-learnable components, such as farthest point sampling, k nearest neighbors, and pooling operations. So instead of the typical classification head, the non-parametric network uses similarity matching to predict the logits. Hence, the static memory is utilized to gather the necessary category information from the source domain for similarity matching with target. So to optimize the use of this memory, we apply a herding algorithm combined with the nearest mean selection technique, making sure that only a limited memory spaces is used. Essentially, we just select features that are closer to the feature class average for source data. At test time, the same non-parametric network will also process the test point cloud to extract the feature. However, due to the distribution gap between the source and target domains, making direct predictions through the similarity matrix across two domains could be problematic. These features, along with the static prototype features, need to be first mapped onto a shared subspace before constructing the similarity matrix. So, to approximate the mapping function onto the common subspaces, in practice, we utilize a classical transfer learning technique named Transfer Component Analysis, TCA. TCA identifies a transformation matrix W as the empirical measurement of the mapping function to project both source feature and target feature onto the commonly shared subspaces. And its objective is to minimize the MMD distance on the mapped subspaces. After that, we can construct the similarity matrix on the mapped subspaces to output the logits. Finally, the losses from the non-parametric network will supplement those from the source model through an adaptation module, which uses prediction entropy to determine the final outputs. We calculate the entropy of these losses to assess the model's certainty of the sample, as lower entropy generally indicates higher confidence. This helps to dynamically adjust the response based on the degree of difference between current and source domains. Notably, each module of our BFTT3D, including the non-parametric network, subspace learning, and adaptation, does not introduce any parameters that need backpropagation during adaptation. And here is the experimental result of our BFTT3D. We will show our BFTT3D on two datasets, Mononet 40C and Scan Object C. So each of these two datasets benchmark has 15 common types of corruption shown on the table. So these are induced on the original test sets, and their purpose is to mimic the distribution shifts that occur in the real world. And these experimental outcomes on these two data common benchmark shows that our BFTT is actually effective in adaptation, and also it does not suffer from error accumulation in the adaptation like other baseline methods. Apart from this, here we also show the efficient test of our BFTT3D model. We could see that compared with other baseline methods, BFTT3D does not update any parameters, and it is also very efficient during inference time.